Welcome. This video is titled as non-linear transformation of variables and linear regression models. Why and how? If we remember from basic textbooks on a classical linear regression model, the classical linear regression model is based on a number of assumptions. Therefore, for a linear model to be a good model, there are a number of preconditions or assumptions that need to be fulfilled. And these include number one, linearity. The relationship between the variables can be described by a linear equation. This assumption of linearity is often also referred to as the assumption of additivity. Contrary to intuition, the assumption is not that the relationship between variables should be linear, but the assumption is that there is linearity or additivity in the parameters. That is, the effects of these variables in the model should add up. The second precondition or assumption of classical linear regression model is that the residuals are independent of each other. Another assumption of the classical linear regression model is that of equal variance, and it means the residuals have equal variance, and this assumption is also known as the assumption of homoscedasticity. One of the most important assumptions of the classical linear regression model is that of normality, and it implies that the distribution of the residuals follows normal distribution. That is, the distribution of the residuals is normal. If the aforementioned assumptions are met, then the classical linear regression model works well. It can be estimated with the help of ordinary least squares method, but if these assumptions are not fulfilled, then the standard errors should not be trusted upon, and they should be computed using alternative methods. Let us take an example of the earning functions. Consider a regression of the dependent variable y on one independent variable x1, and let us suppose the estimated model is as follows, where yi is equal to beta naught hat plus beta 1 hat x1i plus vi. Here the dependent variable y is wages, the independent variable x1 is the experience, and v is the error term. The terms beta naught hat and beta 1 hat are estimates of the true population parameter beta 1 and beta 2 respectively. So beta naught hat and beta 1 hat are statistics. They are based on sample, whereas beta 1 and beta 2 are population parameters. These are based on population. If we plot the residuals of this model against the predicted wages, the data points may not suggest a completely linear relationship but a curved one. We will see that when we analyze the data later in this presentation. This problem of model misfit could be solved by not only using experience as the explanatory or predictor variable, but also the square of experience, that is experience squared. For each observed value of experience, we compute the square. This new variable, let us call it experience squared, and if we add it to our regression model, the least squares regression equation then becomes as follows: yi is equal to beta naught hat plus beta 1 hat x1i plus beta 2 hat x1i square plus vi. Now this model includes experience as an independent variable, and then it also uses experience squared in this model. If we then plot the data and the regression line, we may see that the regression line goes straight through the points. Note that the regression line, when plotted against experience, is non-linear, but equation itself is linear, that is, there are only two effects added up, one from variable experience and one from variable experience squared. We may also see from the histogram and the residuals plot that the residuals are randomly drawn from a normal distribution and are not related to predicted wages. Thus, our additive model with effects of experience and experience squared leads to a nice fitting model with random normally scattered residuals. So for this purpose we need transformation of variables to achieve linearity. Transforming a variable that may be independent variable or dependent variable involves using a mathematical operation to change its measurement scale. And broadly speaking, there are two kinds of transformation. One is linear transformation and another one is non-linear transformation. In linear transformation, it preserves linear relationships between variables. Therefore, the correlation between x and y would be unchanged after a linear transformation. Examples of a linear transformation to variable x would be multiplying x by a constant, dividing x by a constant, or adding a constant to x variable. Non-linear transformation changes, that is, it increases or decreases linear relationships between variables and therefore changes the correlation between variables. Examples of a non-linear transformation of variable x would be taking the square root of x or the reciprocal of x or the log of x or some other kind of, or taking the square of the variable, the x variable. In regression, a transformation to achieve linearity is a special kind of non-linear transformation. It is a non-linear transformation that increases the linear relationship between two variables. In order to see that, we will use some data, and we would prove that if we introduce transformation, non-linear transformation in the model, it improves the results. So, summing up this discussion, it can be inferred that the relationship between two variables need not be linear in order for a linear model to be appropriate. A transformation of an independent variable or a dependent variable, such as taking a square, can result in normally randomly scattered residuals. The linearity assumption is that the effects of a number of variables, transformed or untransformed, add up and lead to a model with normally and independently randomly scattered residuals. In order to prove this, we are going to use Stata data and use the nonlinear transformation to prove the aforementioned claim that it will improve the results or the output of the regression model. So, to do that, let us open Stata, and here I have already opened my Stata file. First of all, I would describe this data, and there are a number of variables. So, to do this, I have already made a do file, so I'll use that. So after all this opens, I'll explain this. So let me start with the regression of wage on experience. Now this is my regression output. These are the models, levels, statistics. This is the ANOVA, and this is the coefficient of experience. This is its standard error, its t-value, its p-value and 95% confidence interval. In this model, we have assumed that there is a linear relationship between a wage and experience, and we may explain this that one additional year of experience leads to 54-cent increase in wage. But if we check this, then the relationship between the age and the experience may not be linear. Let me show you two-way scatter of wage and experience. So if you look at this scatter plot, this scatter plot is not linear. It shows that this is a curved type relationship. This is like this. This is going like this. So this is not perfectly linear. That is a kind of non-linear, or you may say a curved relationship. After this, let me also check the histogram of wage, and the histogram of wage with the normal distribution. So I'll use this, and if you look at this histogram with the normal density function, it seems that this is not really a normal distribution. It's somewhat skewed. So this is the eyeball guess. So this is not normal. Later on, we will also use some tests for normality of this variable. After this, we may also check the histogram of experience with the normal density function, and again this time we have left skewed or negatively skewed distribution. This is not normal distribution. So using visual analysis or histogram analysis, we may guess that both of these variables are not normal, and the scatter diagram showed that the relationship between these two variables doesn't seem to be linear. It's a curved type relationship. After this, let us see the skewness statistics, the test of skewness for these both variables, that is wage and experience. And if I press, it gives us skewness of both the variables, that is wage and experience. Now the wage variable is not normal. This is more than 2. Usually for a systematic distribution, this skewness value should be 0, but this is much higher than 0. So this is the distribution of the wage is skewed, that is positively skewed. Similarly, the distribution of the experience variable is negatively skewed. This is also not 0. So after that, let me check if I have already taken the log of wage. So I will check the two-way scatter of log wages and the wages, that is the log of wage against the actual wage rate. So this means that this relation is like curvilinear. It's not linear. So this is one proof that the relationship is not linear. And after that, we may also check the skewness test of the log of wage and the wage, and when took the log of wage, the skewness value decreased from 2.007325 to 0.39. So this is not exactly equal to 0, but it is close to 0. So that is now it shows that if you take the log of wage, then the distribution of the log of wage is almost normally distributed. After this, I will make scatter of the experience square and the experience, and let me see how does it look like. So this is also not perfectly linear. This is also carved type relationship between experience and experience squared, and the relationship between between wage and wage squared was also curved shaped, not perfectly linear. And we can also check do this one, and this is the scatter diagram of log of wage and experience squared. And now this relationship, although it's not completely linear, but this transformation of the two variables, we took the log of wage and we took the square of the experience. Now it improved the relationship between these two variables. So after this, I would like to run another regression in which I regress log on experience and experience square. So experience and this is the now when I use this regression, the command is regress log of age on not only experience but also on the square root of experience. So C means that this is a continuous variable, and this hashtag icon means that we have multiplied the experience by experience, so this is square. Now this is the model level statistics. These are model level statistics. Total number of observation 526. This is the analysis of variance, and this is the output of the regression. The dependent variable is log of age, and this is experience, and it has a negative sign, and this is the experience square, it has the positive sign. And although this is not completely significant, but slightly almost significant at 5% level, but the experience squared is significant highly, and this is the consumption. So this means that initially the log of age decreases with the experience, but after some time it is increasing at increasing rate. It then increases at an increasing rate. So after this I will predict. Let me see if I have already predicted. No, I will predict wage height. So I predicted this. So after this I will make the scatter diagram of log of the predicted value of height and experience. So let me see what does it show. That should be experience squared, I think, if it is. Okay, ladies and gentlemen, since this is not working, so we can guess from this regression model that we transformed both the variables. The left hand side variable was transformed by taking the log of wage, and the right hand side variable experience was transformed in such a way that it is entered in this model in two ways. One is experience itself, and secondly experience squares. And now the output is very good, and it shows that the the initially with the experience log of age decreases, but later on it increases at an increasing rate. Let me also check if I could make this graph of scatter diagram of create. This should be my dependent variable, should be log of wage, and this should be my wage at, and let me see, let me take this as experience. What does it, but then after some time there is a continuous increase in the wage along with this experience squared. So what we did, we basically transformed the experience to experience square, and we also transformed wage into log wage, and now you see that the result is very good, and that is how non-linear transformation improves the output of the model. So this result is exactly what we showed here in this diagram. So ladies and gentlemen, this is how we improve the estimation of the model, the interpretation of the model by transformation of the model. So kindly subscribe the channel, and do not forget to click on the bell icon, and you will receive notification about my new videos that I'll upload for you. Thanks for watching.